Issue. Hi, good morning, everyone. We are going to wait for a couple of minutes and then we'll start the session. All right, so it's 11 a.m. and we will begin now. So good morning, everyone. I welcome you to the fourth webinar of Simulations with DesignBuilder webinar series. I am Amanda and I will be moderating today's session. So in this webinar, we will see how we can evaluate the air conditioning loads in buildings and how we can use load calculations for system sizing. We will also explore energy savings through various types of HVAC systems and demonstrate how to model unitary systems. Next slide, please. Before we begin, I would like to thank our program supporters and affiliates for this year. These organizations have provided immense support to Solar Decathlon India and catalyzed our transition to a net zero future. We have with us today Mansi, Parikh, and PC Thomas. Mansi is a senior sustainability consultant working in the field of sustainable design. She has key qualifications in the field of passive designing, low energy cooling and HVAC systems, lighting and daylighting design. She has worked on various projects with goals leading to net zero energy, water, and waste. Hi, Mansi, good morning. We also have PC Thomas here. PC Thomas is the founding director of Team Catalyst and also an adjunct associate professor at the University of Sydney. He specializes in integrated building design, using simulation tools to assist in design and delivery of sustainable buildings, in particular in predicting the performance of mechanical services. He has a master's degree in mechanical engineering, 30 years of consulting, research and teaching experience in sustainable buildings, building energy simulations, energy auditing, energy efficiency in buildings, and solar energy. Hello, PC. Hi.
Hi, Amanda.
So we will begin with the presentations now, and to all the participants, please feel free to send in your questions anytime during the session. We will take as many questions as time allows during the session. And with that, let's get started. So over to you, Mansi.
Hi, thank you, Amanda. So in this session, we'll be discussing about the internal and the external loads in the building and the impact on it and the impact of energy conservation measures on system sizing. And we'll be also covering the reduction in cooling loads. So what are HVAC loads? So what are heating or cooling loads? So heating and cooling loads are measures of energy needed to be added or removed from a space by HVAC systems to provide the desired level of thermal comfort in a particular space. So the right sizing of HVAC systems begin with accurate understanding of heating and cooling loads in a particular space. So there are two kinds of cooling loads, I would say, specific to Indian climate, where there would be only external and the internal loads. So external loads directly depend on the location and the climate type. They are impacted because of the solar radiation, outdoor temperature, and humidity. So heat gains in the building, which is directly proportional to So heat gain in a particular space is directly proportional to cooling loads. They are caused due to conduction from roofs, walls, glazing, the convective heat transfer through infiltration, through cracks, radiative heat transfer through roofs, walls, and windows. So these are the kind of external cooling loads. Also, a well-designed envelope can intervene to reduce these cooling loads. Now, these are the internal loads. Internal loads are generated by people, lighting, and equipments. So these are also sometimes called as internal gains, as you might have seen in the as you might have seen in the DesignBuilder terminology, I would say. Lighting and equipment loads are sensible heat, and the metabolic heat generated by occupants are basically a combination of sensible and the latent heat. So there are three types of internal loads: lighting, people, and equipment. Again, these is an assumption sheet for a cooling load calculation, which we do for a typical office building. That would have that these can be assumptions. These are noted down for occupancy, lighting, and equipment. Where the occupancy was taken. So for this particular project, we took the occupancy from the architectural drawings and layouts. Lighting load as per the ECBC standard or ECBC super buildings, I would say that was around for a typical open space office, it was around 4.5 watt per square meter. And equipment wattage as per the market survey for efficient equipments, or probably be 5-star rated fans or be 5-star rated microwaves in a case. So that was taken in an account, and this was discussed with various consultants and client on board to get the realistic figures for load calculations. As you can see, load calculations or HVAC load calculation are very much important in a project, because that would account for the system sizing in a project. So say for a typical office building, for a typical space, there would be internal and the external loads. Based on that, the tonnage of refrigeration would be derived. So to get the right size for the tonnage for a particular space, these load calculations has to be done, and the inputs has to be very specific and should be as realistic as possible to do the right size, to do the right sizing. Else, at times, these systems get oversized And that has an implication on the first cost of an equipment. So say for a split unit, if you go for say 2 TR, it is going to cost you around 25,000. And the same split unit, so split AC unit, if it is for 4 to 5 TR, it is going to cost you almost 2 to 3 times. So that would be around 60,000. So there is a cost attached to a system sizing, I would say. So for a larger project, we do these kind of sheets or checklists where we incorporate various components like, set point, humidity, occupants, fresh air, equipment details, lighting, LPDs. All of these are, put together, and this sheet goes to different consultants. So to ensure that everybody is on board, and this is kind of a checklist which we keep for more or less each of the project. After the load calculations are done, for this particular project, we checked for the zoning of the building. Thermal zones are nothing but thermal zones define thermal zones are defined by the location where they are located in a particular space. They are dependent on the temperature, humidity. They have to be defined in a way. So as you can see, there are two kinds of thermal zones, more or less. That would be perimeter zones and the core zones. So as you can see, for this particular building, we divided them into a part where the ones in the red were defined as a perimeter zone because they were directly in contact with the external surrounding. And the other part in the blue here, you can see are the core zones because they were between the two of the conditioned spaces. So the red ones are the conditioned spaces. This is a typical office building. The red zones are the office spaces, and the blue ones are the core zones. They are again office spaces, but however, they're in-house, or I would say they are in between of the two conditioned spaces. And the white ones which are left, those are actually naturally ventilated spaces. So after this, there has to be assumptions again with the heat load calculation. There has to be assumptions for the schedules. So in the previous part, what we saw was, we have to do. We had the assumptions for internal loads in terms of equipment, lighting, and occupants. There has to be schedules which are set. So these are the kind of schedules which are created for typical kind of spaces for occupancy, equipment, and lighting. On the left side, you can see is the calendar. So, here more or less, since it's an office building, it was 5 days operation. So this was kind of calendar which was set and fed into the simulation software. Now, HVAC loads, why the load calculation is important, as I specified earlier, that it has an impact on reducing the first cost of an equipment. So first cost of an equipment, how I explained in the split AC unit of 2 TR and 4 TR. So there are various energy conservation measures which we incorporated in this project to reduce the amount of system sizing, to reduce the cooling load in a particular space. So for envelope, they were measures for insulating walls, roofs, and glazing, for effective coating, reflective coating on the roof, shading design, so sort of chhajjas on the roof, chhajjas for the glazing. Lighting measures also reduces the cooling load. So measures like daylighting design, reducing the LPD in a particular space, that would reduce reduce the heat gains in a particular space. So these are the measures which we use for this particular project. So here in this chart, on the left side are the energy conservation measures for the windows, roof, and walls. And these are the percentage savings in the HVAC load, in the HVAC load. So this is percentage savings on the TR, tonnage of refrigeration required in a particular building. So as you can see, that window measures or glazing measures has maximum impact in terms of load reduction in TR. That was around 24 to 26% for this particular building. For the roof, it was by insulating the roof with almost 100 to 125 of insulation XPS, where we reduced the U value of roof to almost 0.2 watt per square meter per Kelvin. We got reduction of almost 7% in cooling loads. Further, the wall measures by insulating the wall with U value of achieving U value of 0.44, which required almost 50 of an insulation of XPS with a typical brick wall, we can achieve savings of 5%. So how this will account in the reduction in the first cost? We'll see next. So, there are incremental costs for a particular energy conservation measures, which are these. The net incremental cost calculated would be incremental cost of an ECM, when we are so having, say for a wall, adding 25 or 50 on XPS, it's going to add a cost minus reduction in system sizing because of load reduction. So because the first, say, what happens is here in this case, when we add 50 on, if we add, so this is an example, if we add 50 of an insulation to a brick wall, we can get almost 3 to 4% of reduction in the cooling load. That would account in reduction of 2 to 3 tons in a particular space. That 3 to 4 tons of reduction in tonnage can be directly proportional to the cost. So say if air conditioning cost per TR is around 2,000 rupees to 4,000 rupees per TR for a really large space, then that would directly proportional to the reduction in the first cost of an equipment. So net incremental cost calculated here is incremental cost because of the ECM minus cost reduction in the system sizing. So these are the net incremental costs for envelope measures, which was calculated for assemblies of wall, roof, and window. So as you can see that on the one in the pink, that is incremental cost, and the ones in the blue bars are the cooling capacity savings. So that is reduction because that would be the reduction in the first cost of an HVAC equipment because of reduction in the cooling loads. So here, as you can see, for typical wall assembly of 0.9 U value, the reduction in the cooling capacity saving is almost half as compared to the incremental cost. So this is how the calculation was done, and based on this, we evaluated and selected various assemblies of wall, roofs, and windows for this particular project. And here I would like to end my presentation.
Thanks, Mansi. Thank you so much. We have questions. So let's take them up one by one.
Before you do that, Amanda, I have a quick question, if that's all right.
Sure. Yeah.
Mansi, are you able to send me a PDF of what you just presented? I would like to refer to some of those numbers for lighting and equipment when I do the next presentation for DesignBuilder. And the one question I had was that in your outside air, you have got, did I see CFM per square foot, or is it CFM per square meter there? I didn't catch that.
So that is calculated CFM per square foot.
Square meter?
No. So that was basically, so this is probably input data sheet you're referring to, I would say.
Correct. Yes. I just want, so that when I talk, I will connect what you said to what I want to put into DesignBuilder.
Definitely.
So yeah, if you just send me the PDF, I'll work it out from there.
Definitely. I'll share the PDF with you.
Thank you. Sorry,
Okay,
go ahead,
so,
Amanda.
Yeah. So first question we have is, how do we look at our simulation results from DesignBuilder to do HVAC system sizing?
I think we can handle that
Yeah,
in the next.
I think PC will cover this. So we'll move to the next question. Since our building is still in design, how to get the equipment loads? We don't know what the users will put in.
Interesting question. So, there has to be an estimate of what would come in. So say for a residential setup, if it's a residential building, then we know that for a particular space, so like a bedroom would have minimum of equipments would be coming in, would be plug load specifically. There would be charging facilities required for a phone. There would be laptop usage. So you will have to estimate based on these. There has to be assumptions which has to be made. Say for a kitchen, there would be definitely electric kettle, there would be microwave, there would be fridge. So based on that, we go for the efficient equipment, we check the wattages, and based on that, we do the calculation for equipment, I would say.
Right. And I think they can also, talk to their project partner or the clients to get more understanding of what they would need for their building or the project.
Absolutely. Yes.
So next question is, so not perimeter zones don't get any heat gain from outside. So I think this zoning related, you're explaining of, the perimeter zones. So it's asking if the non-perimeter zones will not get any heat gain from outside. Yeah.
So those are the core zones. So core zones, again, so perimeter and the core zones are specifically designed for a building which is going to be air conditioned. So specifically for say core zones, they are all on all the sides, they are surrounded by perimeter zones. So there won't be any sort of interaction of core zones with the outside, I would say. They will be directly interacting with the perimeter zones.
Next question, what will be core type spaces in apartment building?
In an apartment building? That seems like an interesting question. So that depends on which are going to be the conditioned spaces and which are not going to be conditioned at naturally ventilated spaces. And so probably say if it's going to be whole apartment is going to be conditioned, then probably the outdoors, so all the bedrooms which are facing or the living rooms which are facing on the external parts, most cases, because they have to be provided with windows and balconies, there would be spaces like corridors which are in between, that can be core zones. However, this is very specific to if it's going to be naturally ventilated or conditioned and the layout of the particular apartment block, I would say.
Right. Okay, thanks, Mansi. Taking up the next question, what is the best window for reducing HVAC tons in Delhi?
Best window. I think you'll have to do a couple of simulations to check this, I would say. Probably PC can take up this question. So we'll have to.
Yeah, I don't think you can have one specific window that's the best for all projects. You have to choose which window it is, depending on whether it's hot or cold, or you have lots of window or very little window. There's many issues.
Yeah. And sometimes it even depends on the direction that your window is facing.
Correct.
Yeah, right.
These has to be absolutely be checked with simulations.
Right.
Which would be the best type.
Okay, taking up next question. So can I get a link for previous webinar of simulation with DesignBuilder? Yes, you can get. It's also streamed live in our YouTube channel. You can take a look there as well. Next question, how to get cost reduction in system sizing? Does DB has cost? Maybe Mansi, you might, DB obviously doesn't have cost, but
well,
Mansi,
I think
maybe.
It's got costs for fabric, but it's in Great British pounds. So I don't think it's going to be very useful for you guys. Yeah, we had talked about it, but I think the cost changes in every location. So I think it's very location specific to do that.
Right, yeah. So Mansi, would you like to answer this? Because your thesis was where you had done an intense study on this. So
definitely
give direction to them, yeah.
Sure. So, for each energy conservation measure, what I did was did a market survey. So, if you want to understand the cost reduction by incorporating insulation in a particular wall, okay, say if there is 40 insulation which will give you U value of around 0.63 or so, then we'll have to do the cost calculation for that particular insulation. That would account for the reduction, and then there would be cost reduction in the system sizing, because that would be that we can get from the simulation software. uh, Based on the tonnage reduction, and then based on that we have to calculate the net incremental cost, as I said as I discussed in the webinar. So it's not as difficult, I would say, but there has to be a little bit of market survey which has to be done to calculate the net incremental cost. So incremental cost because of the incorporating of particular ECMs, and a little bit of simulation, and we can get this data out.
Mansi, for your thesis, did you kind of speak to people, the industries, or something that you want to add?
Yes.
Like from where exactly did you get the cost information? So maybe that might be helpful if you add that. Yeah.
Sure. So thank you for reminding me, Amanda. So I talked to a couple of industrial partners. So for insulation, I went to probably insulation manufacturers and vendors to talk to them. So for HVAC related things, I contacted Daikin to get the cost out. For lighting, I contacted Schneider. So different vendors were talked to arrive at these particular costs, I would say.
Next question. Is system cost reduction more than incremental? If system cost reduction is more than incremental cost, will net incremental cost be negative? So do we get money back?
This is very interesting, actually. One which my professor used to always had a debate on. So yes, so definitely. So if we don't get money back, but there has to be, so there are ECMs specifically which have negative net incremental cost. Say one with, from my finding, it was more or less the glazing ECMs, because the energy, because of the cost savings were almost 25% in terms of reduction in compared, reduction in terms of TR. So that was a negative incremental cost. There was again an ECM like providing a particular shading device, which had a negative incremental cost, because the amount which was spent for that particular ECM was, 3 to 4% less as compared to reduction in system it offered in the system sizing, I would say. So yes, there is definitely a possibility of having the negative net incremental cost.
Next question, are there standard load numbers for different equipment that we can reference?
Different equipment for India specific, I remember there are papers which talks about loads in watt per square meters for different kind of spaces, be it office, residential, which they can refer to. However, equipment specific, they'll have to do a little bit of market survey.
I think the general numbers that were in your slides, Mansi, I think they were pretty good. They gave you the watts per meter squared for equipment considerations in typical, I think, super ECBC type buildings, isn't it?
Okay. So those were specifically, yes. So the equipment numbers which I use are specifically for ECBC super type of building. LPD you can get from ECBC manual, but equipments, I would say we'll have to do a little bit of market survey, as you said, PC. We did that for this particular project.
Okay. And this was I saw some numbers. You had one desktop per 12 square meters, and the equipment numbers are for that sort of occupation density. Yeah.
Okay, moving on to the next question. The model in my design builder considers my analytical spaces as broken with spaces in between. I am not able to rectify that, and hence I'm not able to simulate anything. So we'll take this up later, PC, maybe?
Yeah, well, I mean,
Want to?
I think we might do that offline.
Right, yeah.
Yeah, there are a couple of other students also who tried to get in touch with me.
Okay.
I think it might be best if you arranged a kind of drop-in session where we could have a look at some design builder issues and try to solve them rather than do one at a time when people come. We can organize a 1 hour and whoever has got some issues, we can try and sort it out.
Yeah, so this question is from Anurag. So Anurag, I would request you to write to Uday regarding this issue, and to everyone as well. If you have any issue, please do write to Uday, and we can set up some kind of a session with PC to kind of resolve the issue. Yeah. Okay, so last question, how to get cost resulting from tonnage reduction?
Interesting question. So as I explained in my webinar, for a particular space, if the tonnage of refrigeration required is 4 tons, okay, now that would say if the cost of tonnage per refrigeration for assumption, say, is 10,000 rupees. So that would cost around 40,000 for 40,000 for a 4 tonnage of refrigeration required. Now, by incorporating a wall measures, or say specifically window measures, the glazing, if that is reduced and the tonnage required for refrigeration is now 3 tons, then that would account for, then the new tonnage would be 3 tons, and that would cost around 30,000 rupees. So the cost resulting in tonnage reduction would be 40 minus 30. So that is 10,000 in terms of savings, I would say, because of incorporating glazing measure in a particular space. So.
Cool. Thanks, Mansi. I mean, it was a really helpful session. We always get stuck after the results. Now what? So maybe your session was very helpful in understanding how to move ahead. Cool. So we'll move ahead with PC's session now. And please feel free to ask any questions in the chat or in the Q&A window. We can take up in between as well if time allows. Yeah. Thank you, Mansi. Yeah.
Thank you, PC. Thank you, Amanda.
Thanks, Mansi. If you can just email me that PDF, I might use it in the lecture now.
I'll do it right away. PC.
All right. Thanks so much.
Thank you.
Okay. So maybe before we start, can I please get an idea of how many people on the webinar are actually having some air conditioning subjects, so mechanical engineers, chemical engineers, any of those kinds of people? Have you had any experience at all with cooling load calculations or sizing fans and pumps and things like that? If you can just indicate to me, maybe on the chat, that'll be useful for me to know. Okay, so while that's happening, what I've done, and let me share my screen, is let me know when you can see my screen, Amanda. Can you see it?
I can see it, yeah.
Okay, perfect. So I have set up a model, and I'll explain to you how we're going to do this. So if you look at this particular model, I've actually set it up for Delhi, and I've used the all the weather parameters for Delhi. So hopefully that will be useful for you guys. Okay, and what I've done is at the location tab on the top there, if you go to the location, then you'll see here there's something called the summer design weather data. and something called winter design weather data. Okay, so we're going to look at the summer design data. Now, before you actually start to calculate the loads, you have to have an idea of what it is that you're going to design for. What weather condition are you going to design for, right? You can't design a system for an infinitely large weather condition. Then your system will become infinitely large, and that's not possible. So if you look here, you'll see that there's a couple of things in here. There is a 0.4% monthly design dry bulb temperature with a mean coincident wet bulb temperature. So we call this a dry bulb temperature priority design condition. And this 0.4% means that we expect that this combination of design conditions, weather conditions, are not exceeded by more than 0.4% of the time in a year. And that's done by looking at, 10, 20 years of historical data and trying to work out what is a good design condition. In this case, these design conditions are listed in ASHRAE, and ISHRI will have something. I'm using the ASHRAE conditions. They're programmed into DesignBuilder, so you don't have to worry about it. Now you'll see that there's a dry bulb condition. There is what we call a coincident wet bulb condition. So at this dry bulb condition, what is the humidity in the air? Okay, so if you take a psychometric chart and you look at the combination of dry bulb and wet bulb, you will get a particular point on the chart. Okay, and the third item that you get there is what is the minimum temperature in that day. So if you say, you can see here that May has 45.2, June has 46.1, and at the same time, the coincident wet bulb is 22.5, 24.5. And this one gives you the minimum temperature of at night. So you can see here that that's a really uncomfortable day. It goes from 45.2, and at night you're still 31.4. In June, you're 33.9, which is really quite uncomfortable condition, right? Now, depending on what kind of project you're designing for, you might say that, look, it doesn't matter, 0.4% is very stringent. I don't need it to be that stringent. You have some options. Okay, so here is one that says you are okay if it's exceeded 2% of the time. So what you're telling your client is 2% of the year, my air conditioning system won't be able to keep the thermostat settings. It will drift a bit. Now, if you're okay with that, we can significantly reduce the size of our air conditioning system and therefore the cost of that system. Okay. Now, as you can see, there are some more items below that. Okay, so you have 0.4, 2%, 5%, 10%. Then you have another set here, 0.4, 2, 5, and 10 again. And in this case, if you read it, it actually says monthly design wet bulb and mean coincident dry bulb. So if you are designing an air conditioning system in a humid location, Chennai, Mumbai, Trivandrum, then you have, the air is very humid. And when the air is humid, it takes more energy for dehumidification. And therefore, you need to test the sizing of the system with dehumidification duty. In that case, you need to choose one of these four. Okay. Now, For what we're going to do today, I'm not going to change much. I'm going to leave it at the most stringent, 0.4%, right? So that's what I've selected, okay? Now, be careful before you do that. You should go in and you should look at the ground temperatures, and you will need to add the correct ground temperatures for your location. Now, you can get that from Climate Consultant, or you can even get it from the weather file that Energy Plus uses. If you go and look for the EPW file, the Energy Plus weather file, that actually has got it. And I'll show you. This is New Delhi, the ISRAE file, you can see here. And there's a file called a stat file, which you can find. And in that stat file, you will find these ground temperatures, okay? It's most important if you have a small building which is sitting on the ground, like a residence, okay? Then your ground temperatures need to be correct. If you've got a very large building and if you've got a basement car park and actually none of the conditioned areas sit on the ground, this is less important, okay? But you must be aware of that and you must put that in before you make a load calculation. Okay, having done that, then the things that Mansi has just talked about, we need to address, okay? And if you remember very early on, I think it was in one of my first lectures, we looked at this particular slide here, which I'm going to just show you. And you'll note that these are the same loads that Mansi was talking about a few minutes ago, okay? So we talk about heat from solar radiation or heat gain from solar, which comes through the windows. We talk about the heat that is generated by internal equipment. Mansi told us, I think if I remember right, she had 100 watts per desktop computer, 30 watts per laptop computer, etc., etc., etc. Okay, and there are two other things. There's equipment loads, there's lighting loads, and there's heat load from people, okay? So we need to account for those things. Then, of course, there is the load, which is conduction load, or again, which Mansi talked about. That is usually because of a temperature difference between inside and outside. And if you remember just now when we were looking at the design condition for Delhi, we saw that in June, I think it was, the outside condition was 46.1 degrees. So your temperature difference that you're going to be looking at on that day at that peak time will be based on a temperature difference of 46.1 and whatever temperature you want to maintain on the inside, okay? That's the driving potential for heat transfer, okay? And then lastly, we have the heat from exchange of air between the inside and the outside. And if you remember, we spoke about two kinds. One is infiltration, which you don't want because it's air leaking in from gaps in construction and so forth. And the other one is ventilation air, or the amount of outside air you bring into a space to remove, to provide oxygen and to make sure that people don't get sleepy and so on. CO2 concentrations you want to reduce so far, okay? So those four things we're going to have to set up first before we can do the load calculation. So where do you put these four loads in? Okay, so in the activity tab is where you start. Okay, so in the activity tab, the first thing you tell it is how many people are there. Okay, so what I've got here is how many meters squared per person. Okay, and I remember from Mansi's slide that she was, for that project that she had, I think I remember she said it was one desktop every 12 square meters. Okay, that's quite generous. In Australia, we would probably, in an office, we would say one person every 10 square meters. It might get tighter. I think in India, I've seen numbers as low as one person every 7 square meters. Now, of course, with COVID, that may change. I don't know. But you should go and look at your national building code, NBC. And usually the NBC will tell you how many people or how many square meters per person. And then you start to count the load from that. Okay, so yes, you know that there are, there's one person every 10 square meters. How much heat energy does a person produce? Okay, that you need to put in this thing called metabolic rates. Okay, now again, NBC, SIBC, ASHRAE, ISHRI, they all have standard parameters, and you can go and look at that. We use in Australia something called AERA, which is the Australian Institute of Refrigeration, Air Conditioning and Heating Engineers. And what we've been told is that for us, we have to use a value of 130 watts. Okay, so each adult male will produce 130 watts of heat. Okay. Now, all this heat is not straightforward heat which you can change into temperature. Some of that is what we call latent heat or humidity. Okay, and that 130 watts, you can see that on the side here. We break that up by, again, depending on what they give you, you have to find out. But I'd say it's probably going to be quite close. We're told that 55 watts is latent and 75 watts is sensible. Okay, so in that case, then the model wants to know for load calculation, you've given it 130 watts. How much of that is latent? That's what it's asking me for, this latent fraction. Okay, so if you take that 55 watts, which is latent, and you divide it by the total of 130 watts, you'll get 0.42, which is what I have put. Okay, now you'll find that your design builder may not look like this. And the way to make it look like that is you go to this thing called model options. And in the model options, you can change these things here. Okay, so I've said here I want to have how many area per person. You might say, no, I don't need area per person. I've got number of people in each space. I'm happy to put that. You can do that. Okay, or the default is occupant density. How many people per square meter? So you'll get some funny number like 0.11 person per meter square, approximately 10 square meters per person. You can decide whatever it is that best suits your project, and you can put that on. Okay, I've put area per person. The other one is this occupancy latent gains. Okay, so you remember I've put that fixed fraction, 0.42. If I don't put this fixed fraction, then the option is a dynamic calculation. Energy Plus is really quite smart. It has some really fantastic equations behind it, and it looks at the space and then it works out how much of the people's heat is going to be latent as compared to sensible. Okay, so it looks at space temperatures and then tries to figure that out. But typically when you're doing an air conditioning design, most engineers want to know for certain. So we use this fixed fraction, okay? The other thing, two things you want to think about is, how do you want to show equipment gains? Do you want to show the absolute power in watts? So you can say, okay, in this zone, we've got, 1,000 watts of equipment or something, or you can give it as power density, right? And the same for lighting. Now, in the example that Mansi showed us just now, I remember that for the ECBC Super, the lighting load LPD, I think, lighting power density, was 4.5 watts a meter squared. And actually that's what we have in Australia as well for our minimum energy efficiency criteria, okay? So those things you can put there. Once you've got that all done, and this is building on all the other things that we talked about. So now I have 10 meters squared per person, okay? And then I have a schedule for occupancy. And again, I remember the schedule that Mansi had in her slides presentation. You should go back and look at it carefully, right? So I have a schedule that is similar, but not quite the same, okay? So you can see here that I've got in this compact schedule, I can do everything that Mansi showed in a couple of screens in one command, okay? So I'm saying that for weekdays, until 7 o'clock, there's no occupation, and then it varies. From 7 to 8, it's 10%. From 8 to 9, it's 20%. But this is the critical one. From 9 o'clock to 5 o'clock, it's only 70% of the design occupancy. Okay, now that's not very good. Why it's not good is because when you're doing a design occupancy, you want to make sure that there's 100% occupancy in the space, so that if the space was occupied to its full design capacity, your air conditioning system would be able to take care of that. Okay. So what we can see here is that I have applied that for weekdays and summer design day. And actually for the summer design day, I would like this to be 100%, right? So what I'm going to do is I'm going to make another 4 block. So I'm just going to copy that block there and make a copy of that. So I'll just paste it in there as well. Okay, now I've got 2 blocks. I leave the weekday as it is, because what I'm assuming is that on a typical weekday, when I'm trying to predict the energy use, between 9 o'clock and 5 p.m., only 70% of the people are there. And if I remember Mansi's schedule, I think it said 80%. Okay, so you can go back and check yours. But what I want to do is that for the design day, the summer design day, when I'm going to size the air conditioning system, I actually want that to be 1. So what I'll do is I'll do a little trick. I'll double everything. And for that time period, when it's critical, I'll say 100% occupancy during that time. Okay. And that'll ensure that the system that I design will take care of the worst case scenario. And just to remind myself, I will put a DD over there. Everything else I'm leaving the same. Okay, just for the summer design day, it will run occupancy like this. All right. So now that was people loads. Okay. The other loads we spoke about were, one is equipment. And in this case, In Australia, we typically say 11 watts per meter squared for an office. Okay. And that's basically saying that you have one person every 10 square meters. That one person has got access to a computer. Typically, they're LCD screens. So they're about 40, 50 watts. And then they may have a desktop. So that total of 100 watts that Mansi referred to, that's pretty good. If you're using a laptop, it's going to be less, 30 watts, 40 watts, something like that. There'll be some printers, fax machines. You may have a little kitchenette or a kettle or something else that uses energy. So you'll have to go around and make some estimates about that. And typically there will be design criteria available for you. Now, my guess is that because India sort of uses two sets of units, you will get watts per square foot, and you'll have to convert that to watts per square meter, because in DesignBuilder and the rest of the world, unfortunately, we stay in one system. We don't mix SI with imperial systems. So you're going to have to do some translation between the two, right? And in this case, this is the equipment schedule. And if you look at the equipment schedule, we really don't have to do anything, because you can see that in that period from 9 o'clock to 1 o'clock, it's 100%, and that's fine for the design condition. So I won't do anything to that. Okay. So that's 2 out of 3. And if you remember, the third one was lighting. So if you go to the lighting tab, you can set up your lighting requirement. And in this case, I've got 4.5 watts meter squared. This is my lighting power density. This is ECBC super value. Okay. And again, if you look at the lighting schedule, you just want to confirm that during that 9 o'clock to 1 o'clock, to 5 o'clock, and there it is, 9 o'clock to 5 o'clock, it's 1. So 100% of the design value for lighting power density is applied during that time. So I don't need to do anything for that. Okay. Now, once you've set up all these things, and by the way, I've applied this at the building level. You want to make sure that they've been correctly carried over at each zone level. If you've made any custom adjustments, you need to be aware of that. And you can see here, it's taking the correct values. 10 person per meter squared, 0.42 latent fraction. Oh, here we go. This is not taking 11, it's taking 15. Okay. So what I need to do is to try and see if I can default it back to 11 watts. And you'll have to do that for every zone. You'll have to do a check to just make sure that you can do that. Okay. And once you do, hopefully, yeah, that's come over there. I'll just make sure it's, I need to default that back as well. Yeah, so now I'll do a random check. Yeah, that's okay. I'll do this one as well. Down to the top level, and I'll do another random check. That's good. Now, if you look at the way that I've named my zones, the interior zones are what Mansi called core zones. Okay, same thing. So it's an interior zone. It is surrounded by perimeter zones. Okay, and if you go back and look at the layout of the model, if you look at any floor, so let's look at the first floor, you can see that's how I've set it out. Okay. So this is the north zone. This is a west zone. That's unconditioned, so I haven't given it a orientation, but it's really an east zone. This is west, this is south. I've named that southwest for some reason. That could actually, okay, I should probably call that southeast. So let us change that. And probably that means I should change the names for all of those others as well, just so that we don't get confused. Okay. There we are. Southeast. I don't know if I didn't change that or whatever. Let me just see where this is. That's north. This is west. West. Ah, here it goes. So this is the southeast zone. Northeast will become the southeast zone. I'm sorry, in Australia, the orientation is completely changed because we're in the southern hemisphere. So when I changed it, I must have missed it. This is south, this is west, this is south. Yeah, this is all looking good. All right. So here's my building. We've adjusted all those internal zones, the internal loads, beg your pardon. We've put some thermostat settings. So here I put 21.1 for heating. We're not going to be that interested in that. We're really interested in the cooling thermostat, and that's 23.9. Now, you may want to change that, okay? And that's okay. So if you decide that in India, you're okay with having 26 degrees, fine. You can change the number, okay? But what I'm going to do at this point is, okay, I need to show you one more thing before we rush off. I don't have any detailed air conditioning. So you can see here, I can't see any HVAC here. If I go to this HVAC tab, I need to choose a type of air conditioner to do this simulation, okay? At least an ideal type of air conditioner. And for small jobs, I suggest you choose a unitary heat pump. That's the same as a split system that can do heating and cooling, okay? And then the other thing that you may need to do, and we'll come back to that in an instant, once we've done the first set of runs, we may decide we want to think about how we want to design the air conditioning system. That's why I was asking, is there anybody in this who has done any sort of air conditioning design in your studies? It's a difficult one because most people who are teaching at universities don't always have practical experience, and the ones who have practical experience don't really know how to teach it very well. I'm kind of somewhere in between, so hopefully you'll find this a bit useful.
PC, I have created a poll question for that. If
Okay.
you want, I can run it right now.
Yes, please. That'll be nice. It'll be good to know how many I've got. Yeah.
Okay, cool.
Okay.
So I'm launching the poll.
Okay, great.
Yeah. So
actually, the question to ask is, have you had any HVAC subjects in your studies? Because here you're asking whether you've had a chance to model the system. That's not what I want to know. I want to know whether they've had any actual educational subjects with air conditioning.
Okay.
Maybe you can take this one, but you can also ask a second question on that.
Yeah. Cool.
Okay, no problem. So as you can see here, in the template, I've got unitary heat pump. I've turned on mechanical ventilation, and because I'm doing a cooling load calculation, I will put cooling on. Now you may or may not put on heating. Like in many places in India, we don't do heating, but I have left it on. And I've put the same schedule, if you notice, on all these three. Okay, so ventilation, heating, and cooling. And what it is, it's when heating and cooling and the fan is available. And all I've done for that schedule is really put together a time frame for when it runs. Okay, so in this case, I've just said that for weekends, for the summer design day, for the winter design day, it runs from 7 o'clock in the morning till 6 p.m. at night. Okay, that's what I've done. Okay, and then the other thing you will have to be aware of is you need to know what is this supply air condition. Okay, because that determines how much air you need. Okay, now if you're using a VRF, DXF, split system, unitary system, all of those systems, you really can't change the supply air very much. It'll be somewhere in that 12 degrees range, 12, 13, 14, something like that. Okay, I've used 12. Okay, if you have a lower supply air temperature, you need less air. If you have a higher supply air temperature, you need more air. Okay, if you need more air, you need more fan energy. If you make the supply air temperature too cold, you may start to get condensation. So, you know, there's a kind of balance, because when you talk about cooling, it's all about the properties of moist air. That's why engineers so much, they like the psychometric chart. They're always conscious about how much humidity is there and how they're going to deal with it. Okay. Okay, so I've already set all this up. Okay, so you will need to spend quite a few hours just making sure you've got all the data set correctly. Otherwise, the numbers that you get will be not very useful. Okay, so now I'm going to go to cooling design, right? And I'm going to run a cooling design calculation. And what I'm going to do is I'm going to ask it to do the calculation on the 21st day of every month. Now, why am I doing that? Because the equinox and the solstice for each, for the 4 times in the year are all around the 21st or the 22nd. And therefore, the solar radiation data, which we haven't even seen, which is in the background in the model, is going to be representative for the peak summer day and the peak winter day, right? And the other thing I'm going to do is I'm going to say, well, you do the calculation for every month from January to December, because we've got the data, we might as well cycle through. Typically, most consultants will do it for the summer period. So they may say May to July or August. But sometimes, depending on the mass, the glass, the shading, the insulation, you will have some zones peaking in some odd months, okay? So it's good to have a calculation that does every day. Now, I'm not going to put any oversizing. I'm going to ask for the correct sizing. So my design margin is 1, okay? I'm using the ASHRAE heat balance equations to do the calculations, and the airflow is going to be based on the sensible load only, because that's generally how mechanical engineers size the airflow, okay? And that's why I said you may need some theory to back up the air conditioning design that we're showing you. So if I hit OK, it will go away. And it will cycle through a design day for every month. So it will tell me January, February, March, April, it'll cycle through each one, okay? So we'll give it that, and in the meanwhile, let me see if I can, okay, question. Okay. So good questions all. Let me quickly say, who will give us that cost per ton reduction? Are these numbers available? Actually, they're not. Then they're very dependent on each manufacturer. So sometimes, particularly when you're buying larger size chillers, they come in specific sizes. So if you are not able to reduce the heat load below a particular standard size of chillers, and if you got more than one chiller, then you can make up combinations of chillers, then the costing becomes difficult, or the cost saving becomes a bit difficult, right? Now, somebody else asked, can you please mention a demo occupancy schedule profile for a residential building? There are some defaults built into DesignBuilder, but I would really suggest that you want to talk to some people who are designing apartments or houses and try to find out what's useful in your locality. And you may also, I know that there is now an ECBC type thing for residential buildings, and you might want to go there and see whether they have got at least a occupancy schedule that you can use for this. Then Agniba is asked, with ASHRAE 90.1 selected, I'm unable to change the lighting schedule. Well, that's right. When you select ASHRAE 90.1, a lot of things are fixed because they want you to do the compliance calculation in a very fixed way, okay? So they won't allow you to change some of these things. If you want to do your own, you have to go away from 90.1 and do it differently, okay? And then Sunita has asked, how do you decide minimum supply air temperature? Again, that's a question that's difficult for me to answer because every system is slightly different. If you're using a VRF or a unitary system or a DX system for the house, about 13 degrees is quite okay. If you're using a chilled water system, then it's very dependent on whether you're using a chill beam system or a VAV system or an underfloor system. Those things become very critical, okay? Underfloor systems, you can't have a very cold supply air temperature. If you do, you'll freeze the ankles of people. So you have to supply at a much higher temperature, maybe 18 degrees, 19 degrees. When you supply air at that high temperature, you have very little capability of dehumidifying the air. So you can get moist air coming into the space, which is again not very good. So you need to do something before you supply the air for dehumidification, okay? If you're doing chill beam systems, you have to be very careful because you can't let the temperature exceed the dew point in the space, because if you do, then you'll get rain in the space, okay? So if you got a chill beam system, you have to make sure that your construction is quite tight. You don't leak much outside air, and really you lose things like an economizer cycle and things like that. Again, it's quite too much to cover in one quick session. You need to know some HVAC to do that. Please talk to your seniors or your project managers for some of these things. Okay, run complete. So you can see how the loads are. Now for the building, you can see here there is a, you can see here there's hardly any latent load at all. The line actually falls on top of each other, okay? And that's because when the air temperature is that high, 46 degrees centigrade I saw, then the air is quite dry, okay? And so your latent loads become very negligible, okay? Now, let's go to the summary. And in the summary, you can see here, the first thing that I've done is I put this on what's called non-coincident and building level, okay? So if you look at the zones, you can see that I've got 3 unconditioned zones. So it's not calculating the loads for those zones, but it is taking the heat load that goes from that unconditioned zone to the next zone that is conditioned. Okay, from your model, it works that out. But it's giving me the load, the cooling load in kilowatts. Okay, and you need to convert that into tons if you want. And you can do that quite easily. You can just export this data into a CSV file, and you can just use the conversion factors. If you Google convert refrigeration tons to kilowatts, you will get the number. Okay. So here you are. You can see here that the cooling load for that zone, W second 2, West second 2, is 7.46 kilowatts, of which 7 watts is sensible and 0.42 kilowatts is latent, humid loads. Okay, and it's happening at June or at 5 o'clock. And if you look down this, you can see most of them are peaking in either July or June. So most of these are peaking in July. Some are peaking in the morning, some are peaking in the afternoon. Okay, some are peaking late in the afternoon. Okay, so here is 5 o'clock, 6 o'clock. Many are peaking just as soon as the system is started up. Okay, and you can see the total here, 251 kilowatts. Okay, and the flow rate here in meter cube per second, or if you multiply that by 1,000 liters per second. So this is 11,659 liters per second. Again, you can convert from liters per second into CFM, cubic feet per minute. Okay, again, if you Google that, you will get the conversion factor. As I said, in most countries, we use either SI or the Americans use imperial units, but they use only imperial units, or they use SI. India has a kind of mix in between the two. Okay. Now, if there are some interesting things here, one is that you know that this is happening at different times. Okay, so this is the peak load at each zone. So depending on what zone you're looking at, these are all the ground floor zones. These are the first floor zones. These are the second floor zones. Okay. If you go forward, right, there are 2 numbers here which many air conditioning engineers use as check numbers, we call them. Okay. So we get an idea of how many watts per square meter. Okay. In India, you use a value called square foot per ton. We use watts per meter squared. Okay. Again, you need to kind of maybe convert between them. But in our case, watts per meter squared, the smaller the value, the more efficient your design. Okay. So this is a very high west facing zone. So there's very high per square meter load. And you can see here, some of these loads are lower. This is 123. And the internal zones will probably have the least amount of loads. They will be just the loads from the equipment, the people, the air exchange. It's not seeing any load from solar radiation gain. It's not seeing any load from conduction between the outside and the inside. So the loads are much smaller. So 118 watts a meter squared. Compare that to 288 over here, 155, 160. These are all quite strong loads. Okay. Now, there's a thing called gain. Okay, and that's an instantaneous gain of energy coming into the space. If you add up all the gains, it will not add up to the load. And that's why we need computers to do the calculation for us. Because when you say load, it's what the air conditioning system needs to meet. And it's not what's coming through the building fabric and is being generated in the space at that time. It actually is because there is some storage in the fabric of heat, and there is a constant storage and release going on. Okay, so what the air conditioning system sees is delayed and reduced. You know, if you read your Koensberger, very old book, it tells you decrement and delay. And that's what's happening when you look at an air conditioning load. Okay, so if you go to the right, all the way to the end, you'll see all the different components of the gains, right? And right at the end, it will tell you what is the amount of, it's called fresh air, but as we discussed, it's not really fresh air, it's outside air, okay? So in meter cube per second, or if you want, multiply by 1,000, 33 liters per second, 6.5% of the total supply is outside air for this one, okay? If you look at some of the higher numbers, they'll be for the interior zones, because in the interior zones, there's less load. So when there's less load, you require less air, and a larger component of the supply air is outside air. Okay, so there's quite a few things going on for that. Now, one trick I wanted to show you. See, as long as you are devising an air conditioning system which is zone based, so every zone has got its own air conditioning system. So if you have a window air conditioning system, which you stick inside a window, right? And it's only doing that one zone, then you need to size the air conditioning system for that zone. Okay. But suppose you're not, suppose you are doing some sort of a centralized system. You have a VRF system which has got one outdoor unit and it's got many indoor units connected to it. Okay. Then what you're doing is when you add this up, this is actually more than the outdoor unit needs to provide at any one time. Because if you think about it, these peaks are happening at different times. We call them the sum of the peaks, which is the non-coincident load here. Okay. If you want to know what should be the size of this outside condensing unit for a VRF system, or if you're using a chilled water system, a central system, and you want to know what is the size of the chiller, it's actually a little bit less than this 251. You want to find out when does the building peak, you know, when is the highest load when all the other zones are at one time providing to the chiller. And if you click this thing and say coincident, you can see it went down from 251 to 244. That difference is the diversity which you can put in your system. Okay, and it's not a lot on this one. In some buildings, it can be quite big. And you really only need to size your outdoor unit or your chiller for this size. Okay. And you can see that what's happening here, that what it's saying is that in July, as soon as you start the air conditioning system, that is the time that system is going to require the most amount of capacity. Okay. Even though individual zones may peak at different times. Okay, and there's a concept here which you need to try and understand, but once you understand that, it's fine, because in HVAC terms they call it diversity. Okay. Now I did something additional. I actually said okay, and I'll show you that in a second. I'm going to have 3 outdoor units. for this. I'm going to use a VRF system. I'm going to have 3 outdoor units. One is going to be for the entire ground floor. One is going to be for the first floor. And one is going to be for the second floor. That's how I set up this system. Okay. And you can do that too. So I'm going to go back to non-coincident and I'm going to list it by system. So what I did is I created you can see here, there's a ground floor VRF, a first floor VRF, and a second floor VRF. Okay. And these are all the unconditioned zones. I put them into a separate system. That's a virtual system. It's not doing anything, but it's good to group them into a separate system. And if you look here, again, you can see here in this VRF or this outdoor unit, okay, some of the zones are peaking in July at 7:30, some are peaking in June at 6 o'clock, and so on. So you don't need the outdoor unit to be this 78 or 84 or 88. They will be slightly smaller, and you can go and look at it by coincident, and you can see what they are. There's small differences. But when you are sizing the individual zone registers, okay, so when you are sizing the supply air quantity for each zone, you must look at the non-coincident size. That's when that zone is peaking. That's when that zone requires the most amount of supply air at a fixed temperature. And that's how you take these numbers, okay? So I've covered a lot of concepts, right? Hopefully you've caught most of that. Go and talk to an air conditioning engineer who's practicing. He will hopefully be able to understand and describe back to you what he wants, okay? Typically he wants these numbers and he wants it in 3 different ways. He wants that chiller block load or that block load for the condensing unit. Then he wants the individual zone loads, because then he can size the registers for each individual zone, okay? Now, I didn't show you one thing, and that is how to set up this as system-wise. That's actually not too difficult at all. What I did was at each, so I went to the ground floor there, and you can see here the cooling system. And over here, I created a series of systems. So you can see here I've got a ground floor, a first floor, a second floor VRF. And then I added an unconditioned default. I don't want to put any in the default system because there's some calculation error that's happening, which we have spoken to DesignBuilder about. They're correcting it. But if you leave it on default, it does something weird. So don't leave anything on default. Just create an unconditioned default system and stick all the zones that are not conditioned into that, okay? Once you create that, what you do is you make sure that each zone which is being supplied by that system is told that it's doing that here. So if I go to any of them on the ground floor, they should all be looking at the ground VRF, okay? So DesignBuilder then knows, okay, these zones are being conditioned by this system, and it works out the numbers, okay? All right, I think that should be sufficient for you to do design. So that's the load calculation. Obviously, what you'll do is you will make some changes and try out, how these might be impacted. So if you, Mansi, we're showing all those different ones, if you do shading, or if you improve the window performance, or if you make the lighting system more efficient, or if your equipment loads go down, or the number of people that you have in the space reduces, so the number of the amount of heating from them comes down, then the cooling load will come down, okay? So that's something to think about. I won't take up the time here. You guys can try that out yourself. But this is how you do a cooling load calculation in DesignBuilder, okay? So if there are any questions, we can deal with them now.
Yeah, so PC, there are two questions in the chat window. One was from Sunita. Her question was, how are the reheaters sized in HVAC systems?
How are the reheaters sized?
Right, yeah.
Okay, so I'm going to do a detailed air conditioning thing here. And you only need reheat when you are using a like a chilled central system with a boiler and a chiller and a variable air volume type system. So I'll try and deal with it there. I'll just make a note of that. Typically in this kind of system, you can't have a reheat.
Right.
Okay, so VRF systems, you don't really have reheat. What they are able to do is they are simultaneously, in some cases, okay, if you have zones where, or if you have a condition where some zones require heating and some zones require cooling, then a VRF system, which is capable of that. So it's a reverse cycle VRF system with a heat pump that can do that, because what it will do is it will take the warm refrigerant, which comes away by absorbing heat from the cold side. It will pump that directly to the zone requiring heating, and it will use the zone to give the heat away and then go back to the zone that requires cooling. So it's able to do a bit of a refrigerant transfer without sending it to the compressor. Now, that's a bit overrated. Why it's overrated is that if you have a building where you have to have both heating and cooling at the same time, you actually have a very poorly designed building, okay? It's not typical, but there are some instances where you may have a building where some part of the building requires heating and other parts of it require cooling. In India, I think that's quite unusual to have. Many of our locations, we simply have either heating or cooling. If you go down south, you don't have any heating at all. It's just cooling, 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 and the dehumidification. If you go north towards Delhi, yes, you have 2 or 3 months where you need heating, but then very rapidly it transitions back to cooling. Okay. So that's one. Anybody else?
Yeah, one more from the chat window is from Ankit Verma. How to set split AC system of different tons in different spaces? This question.
Of different?
Of different tons in
of different capacities. Yeah, we're going to do that as soon as we get into the next lecture, because
Right,
I'll do one for VRF and one for detailed air conditioning. Yeah.
Okay. Then going back to the Q&A box, is VRF system available in DesignBuilder library file? How to set the diversity factor?
You don't have to set it. As long as you let it auto size, it will do that.
Next question, how to get COP values of different systems?
That's a very good question. Okay. Now, again, let me do the detailed HVAC, then we'll talk about it. See, right now, what we are doing is we're just working out what size of system do we need. We haven't worked out, how efficient is that system or what kind of system. We haven't looked at any of that. I can see there's a question here about multi-zone AHUs and so on. We haven't got there yet. At this point, all we are doing is we're trying to say, what is the load? What is the tonnage, if you wish, based on my building fabric, based on the way that my building is being used, based on the equipment that's there, right? How many people there are, that kind of thing. So first you need to do that. Then you can say, okay, my building behaves like this. Should I use a VRF system? Should I use a central system? Should I use a multi-zone AHU? That's like a different conversation. We haven't got there yet.
Right.
Okay. Now, Sunita has another question here. What is the meaning of latent load in this context? And latent load is basically It's, there are two kinds of heat loads. There's the sensible heat load, which you can feel. So if something is hot, when you touch it, you know that it's hot. So the air temperature, if it's too warm inside there, you want to reduce the air temperature. That is sensible load. Okay. But when you reduce temperature, if the amount of moisture that's being carried in the air is high, because people release moisture, or if you do something like if you do cooking, you release a lot of steam, that's moisture, then you feel uncomfortable because your body tells you something is wrong. The air might be cold, but it's still clammy, it feels humid. Okay, that's latent load, so you need to deal with that as well. Okay. Now I can see there is a question from Vishal about streams and water bodies and
But he says, please ignore the previous question. It was a
Okay.
copy-paste error. But maybe we can take up this one. Can DesignBuilder suggest which is an efficient HVAC system to be used based on input parameters that is fed?
That would be the magic bullet. Then you wouldn't need air conditioning consultants, unfortunately. Yeah, I think that might be. I don't think we actually lack a lot of fundamental knowledge in air conditioning. It is very sad. We have a lot of fundamental knowledge to look at how building fabric works, but we have very, I would say that the people who have good knowledge of air conditioning systems don't have a good knowledge of how buildings work. So because of that, there is a serious disconnect in the industry between those two. And the only way we can get over that is by doing more training for people who are sort of architect engineers who have got skills in both disciplines. We don't really have that in many countries. In some places in Europe, they have architectural engineering degrees, and those people have some of these skills. But in the warmer climates, we really don't have that sort of teaching at all. We have either got building services engineers or we have architects who are interested in sustainability. And there's a big hole in the middle. That's a bit unfortunate. So, okay. So I've taken down that question on multi-zone. I will try to answer that next time. Okay. Are we done?
There's one more question from Vishal.
Yeah.
Does DesignBuilder incorporate any sustainable HVAC system modules as plugins?
I don't understand that question. DesignBuilder has a very flexible approach to how you can design air conditioning systems. So you can, select chillers and fans and boilers and air handling units and VAV boxes and fan coil units and underfloor plenums, but you have to connect them together. It's like you're building fabric. An architect designs a building. I mean, if you ask a person, an architect, why do you need an architect? Why can't all buildings be nice and rectangular? And same question. You can ask the same question of an air conditioning engineer. He has to decide, is this building being used regularly? Is it used, like, for example, if you took a lecture theater or a cinema theater, you have a lot of people come together suddenly for about an hour or 2 hours, and then all of them leave. Okay, what kind of system do you need for that? Something that responds very fast, something where you can put a lot of fresh air in, because when you got so many people in there, it'd be very stuffy otherwise, right? Or you may have like a boarding house, a hotel, for example. In the hotel, most of the guests come there at night. So they all go away in the daytime, they do their business, they go visiting, they go touristing, whatever it is. They come back in the evening, they have dinner, they all sleep in their rooms at night. So what kind of system do you need for that? One that can do cellular rooms, okay? which can manage a little bit of peak in the afternoon because not that many people are there, but certainly needs to be looking after the night cooling. You might find that in those conditions, if it's a humid night, you need to look after dehumidification. What kind of system can you do for that? Okay. So the air conditioning engineer needs to really think about those things. We don't. We just stick a fan coil unit in there and, you know, hope for the best. It doesn't really work that way. And that's why many hotel rooms are quite uncomfortable or can be quite uncomfortable. They're either too cold or sometimes too humid if you try to reset the temperature, right? So DesignBuilder can't, you see, DesignBuilder is what? It's a energy simulation software. You build the model and then you ask for an answer. And then depending on what answer you get, you change your design. If you don't understand what the question is, DesignBuilder can't write a question for you, okay? Now I see this very interesting question. Does DesignBuilder have any interoperability with Rhino, Grasshopper, HVAC tools like Honeybee? HVAC tools and Honeybee and Grasshopper do not mix, okay? Let's be very clear about that. Anything to do with Rhino and Grasshopper is basically fabric. Nothing to do with air conditioning. They don't know how to do any humidity calculations. They don't simulate any, they don't have any components for chillers, fans, boilers, no controls for air conditioning systems, sorry. Okay. You can do very good fabric. You can do very good daylighting. The guy who wrote Honeybee and Grasshopper, they're very good at fabric. Good shading, you know, lovely visualizations of all that stuff. But HVAC, no sir, doesn't work.
One last question in the chat window, PC. Can I calculate load reduction if we have a courtyard or water body, etc., at core of our building?
Where is that?
It's in the chat window.
In the chat window. Hold on, let me just see. I'm looking at the Q&A window. Can I calculate a load reduction if we have a courtyard tree or we're the core of our building? Well, if you have a courtyard, what you're trying to say is that it's a self-shading building. Okay, the courtyard is at the center, and around it, it is creating some shading. That it will pick up. Okay, but if you have a tree and you represent the tree in the model, then the shading provided by the tree, if it's at the correct time, and it provides shading when you have peak need for cooling, yes, you may see some, but generally I suspect you won't. What happens is that you have your highest cooling requirement when the sun is really high up in the sky, okay? And most shading devices may or may not be effective. Well, shading devices that are correctly placed on the north, the south for India will certainly shade the south side. But on the east and the west, a shading device is very less effective because the sun is lower in the sky and it gets in underneath that. So you've got to put some sort of a vertical combined egg crate type shading device at the time when you have the highest peak load. You can watch that by applying some shading device and then recalculating the loads and seeing whether it actually made any impact or not. Many times you'll be surprised, you know, your what you do may have an energy impact across the year, but may not have much of an impact in terms of when the peak load is and what the peak load is. You may still need quite a large system to do that. If you can provide a shading device, for example, if you look at residential houses in Kerala, right? They put a fly roof over the entire building. Now that will work because you are covering the full roof from the sun falling on the roof. Okay, they don't have a winter, so winter is not an issue. They just want to keep the sun off the roof. And interestingly, that started because people were having problems with flat concrete roofs leaking. Kerala gets so much rain that after 5 to 10 years, any concrete slab would leak. So to keep the water off, they used to put a tin sheet on the top. Then suddenly they discovered that their top floors were actually very comfortable because the sun no longer hit the roof. Okay. You will see a big load reduction there because all through the year it's working. You have to come up with some strategy like that.
Right, yeah.
Okay. Water bodies, etc. What the water body does is it modifies the microclimate. Okay. So if you want to account for that in the simulation, you have to create a weather file with the modified microclimate. And then you will be able to see the impact of that. If you use the typical weather file, you're not going to see much impact. Okay. If you use evaporative cooling, yes, you will see some impact. If it's a dry location, it'll be effective. If it's a humid location, it won't be very effective. So you can try that. We have in DesignBuilder, there are evaporative cooling cell deck pads available, which you can put inside an air handler and see how it works.
So PC, that was the last question we had.
Okay. Can you give me 3 minutes? I just want to get a glass of water.
Yeah,
And then
sure.
we can come back and start. So what we'll do, guys, we'll do a VRF system first. And I've actually sent Amanda something that I'd prepared for students in Australia. But as I was running through it, I discovered there are a couple of additions I need to make. So you can start with that, and I will send an updated version within a week or so. But the one that Amanda's got will get you most of the way. Okay.
Right.
So that'll allow you to set up a VRF system, at least from scratch.
So I've
All right.
put the link in the chat window, so everyone you can take a look.
And you might want to follow that as we go through the next session. Okay. I'll try and keep it short because I want to try and do both. And I mean, there's too much to cover, but we'll do what we can.
Yeah.
All right. Thanks. Okay, give me, it's 6:15 now. 6:15 is my clock. I don't know what your clock is.
12:45 now.
10:45. Okay, so 8 o'clock, let's start. Yeah. Sorry, 12 o'clock. 11:45 you said, yeah?
Uh-huh.
Okay, so give me 5 minutes and then we'll go.
Sure, yeah, yeah.
All right. Okay.
Yeah, I can see your screen, please.
You can see my screen? Okay. All right, guys. So first we'll do like what we call a unitary system, a VRF system. That's just variable refrigerant flow. Now, what I might do is just go back to what I showed you in the first lecture. And I sort of said that, okay, this is your air conditioned zone. And to air condition the zone, you are putting in supply air, cold or cool supply air. And you have, the sources of heat in that zone. We talked about that. People, lights, equipment, solar gain, conduction from the fabric, all of those things are there. So this cold supply air will pick up this heat. And then you take it out and you may then do something with the air. Typically, you will exhaust some of it, bring in some outside air, OA is outside air, filter it, make it cold again, then push it with the fan back into the place. Okay. And if you remember, I said that if you got a central system, then the chiller is all this stuff. Okay. So it makes cold water, chilled water, which you then use a pump, you push it through the cooling coil, and then that makes the coil cold, the fan blows it, and so on. And to make that chilled water, the chiller gets hot because it's removing heat from a cold space and it becomes warm. So the cooling tower, if you have a water-cooled system, the cooling tower then tries to keep the chiller cool so it can do its job. Okay. Now, in a VRF system, you don't have these two water loops. So this chilled water loop and this condenser water loop, you remove. Okay. And typically, the compressor, the condenser, and the evaporator are all in the same thing. The evaporator coil is actually the cooling coil. It sits in your house. You have a little white thing on the wall there. And this condenser is sitting outside and there's a fan that's blowing air past it. Okay, that's a VRF system. Now that outside unit, as I said, it can serve more than one indoor unit, and that's what we're going to be looking at. Okay. Now, the other thing I said, if I don't know if you guys remember, I said that you have a control system, whatever kind. And the control system's job is actually quite complicated. Okay. It's like you used a design weather condition. For Delhi, we used 46 degrees as an outside temperature. And so you may have, 100 tons, whatever, so many kilowatts of equipment. But you only need 100 tons when it is 46 degrees outside. Okay. It's not 46 degrees all the time. It's 46 degrees in May or June or July. Okay. For hopefully a week. The rest of the year, it's much less. Solar radiation changes all the time. Okay. You don't need 100 tons all the time. So what's an energy efficient air conditioning system? One that can back off the capacity in an efficient way. So when you only need 20 tons or 50 tons, if your air conditioner can work more efficiently, then that's an efficient air conditioning system. That's different from an efficient building fabric. Okay. Efficient building fabric is insulation, shading, mass, all that stuff. Okay. Efficient air conditioning is how much electricity are you using when you run your pumps, your compressor, all that kind of stuff. And we don't generally make that distinction in what we do, but we should be. Okay. So let's go back to DesignBuilder, right? Now, all this while we were looking at an ideal system. We were just trying to get an understanding of how the building fabric works. Okay. So we know that, if we are going to have an outdoor unit for the ground floor, it's about 78, 79 kilowatts. And for the top floor, it's about 88 kilowatts. The top floor's got exposure to the sun. The middle floor somewhere in between. The ground floor is sitting on the ground. The ground gives you a little bit of cooling. So that's all logical. Okay. Now, how do you actually model a real system? Okay. I'm going to first run this ideal system, then show you a detailed system, and then you can see what the difference is. If I run, and I'm just going to run 1 month in summer, so it's quick. Okay. So we will run, I think it was June or July. Okay, let's do July. So I'm just going to do July, and whatever the output is, I'm not going to worry about it. It should happen fairly quickly because the model is quite simple. So at this point, again, as I said, you are modeling an ideal system. It basically assumes that it can get supply air at a particular temperature and that it can get an infinite quantity of supply air when it needs it, okay, at a fixed efficiency. So that's how you are modeling an ideal system. And as you can see, before it actually does the run for the energy, it first sizes the equipment. Okay, that's why it's auto sized. So once it sizes the equipment, then it runs the simulation. That's what it's doing now. Okay. And as soon as it finishes the simulation, I'm not going to wait for it to load the results. We're going to go directly to the results and look at that. So I'm going to cancel that. And in this case, I'm just going to go and click on View Energy Plus Results. If you've got the result viewer software installed, it will open it up. It's come up on my second screen. So I'm just bringing it across. On this summary page, if you go down, you can see here the end users. Okay. And you can see there's no electricity or gas under heating and cooling, but there's electricity for lighting, electricity for equipment. There's no electricity for fans either, because you haven't modeled any real systems. But you can see here that it has estimated a thermal energy requirement of 44 kilowatts, 44,000 kilowatt hours, I should say, sorry, for the energy used for the month of July. If I went and looked at the hourly results, there's actually going to be a district cooling that it will plot. So the total fabric load, it will plot when you're doing an ideal system, right? So you can see here about 180,000 watts, so about 180 kilowatts for this building. You can look, it's 5 days a week, so Saturday and Sunday, you don't see that. Obviously, you can plot ambient temperature, air temperature, all that sort of stuff. I won't go into that. I just wanted to show you this. Total cooling thermal energy that it's plotting. And if you remember this number, when we come back, we can have a look at it. So this is around 180 something kilowatts, 186 kilowatts, something like that, okay, for this week. Now, when and if you look down here, you won't see any fans, you won't see any compressors, you won't see any indoor units, outdoor units, nothing, okay? Now, so what do we do then? So I go and I'm going to turn on detailed air conditioning now. So if I go to this spanner here, and if I switch it from simple, air conditioning from simple to detailed, and I'm going to leave this as simple HVAC data, okay? And that's what I encourage you to do the same. If you put it to detailed HVAC data, then you have to give quite a lot of extra input to make it work correctly. In this case, what it will do is all the fabric inputs, all the thermostat settings, all the outside air, everything it will take from the data that you've already put in the activity tab, in the lighting tab, and so on, okay? So when I do this, now I've already set up a system, but, and I'll show you that. The document that Amanda has shared right now, that actually explains how to set it up. So if you read through that, there's 6 pages of it. It will give you step by step how to set up a VRF system. And I'd like you to go and try that out. But I'm going to show you how it's set up now, okay? So once I turn on detailed HVAC, there will be this additional thing called HVAC system, okay? And if I click on that, because I've set it up, it will give me a view of that system, okay? And this is what I've done. I've put one outdoor unit, one outdoor VRF unit for the ground floor, one for the first floor, one for the second floor, okay? And if you look here, you can see these X's or crosses next to these things. This one is the outdoor unit, okay? And if I go to the unit itself, I can edit this component, and there's a number of things here about the unit, okay? So most of the defaults for the unit are fine, okay? It's based on a Daikin unit. It's the product of a couple of PhDs that Energy Plus guys did. If you go to the cooling sheet, right, you'll find that there is the size will be auto-calculated. You can change it if you want, but if you don't know the size, it's better to leave it as auto-sized. It will calculate it as it runs. It needs a design COP. What is a design COP? A design COP is at a design condition, and usually there's a laboratory standard design condition. Okay, it's called an ANSI standard, ANSI standard. At that condition, you want the COP. Okay, now manufacturers will play lots of tricks. They will give you, COPs at all kinds of conditions because it makes their COP looks better. Okay, in practice, it doesn't work as well. Okay, so there's a couple of things to remember here as well. It tells you that this system will work from 43 degrees to -6 degrees. So your design temperature of 46 is already higher than that. Okay, so you need to find systems which will work at that design condition, because otherwise some of these systems will actually stop working because of what we call head pressure. The compressor will say it's too much load, I can't work, and then it'll just fail. Okay. Now, it doesn't happen in chilled water systems. Systems don't fail, they become less efficient, but they still provide some cooling. Even if you are 46 or 50 degrees, a chiller will still continue to work. A water-cooled chiller will still continue to work, okay? So these are some things to be aware of. It won't affect you when you're doing this design. It's too much detail here anyway for you. But basically, it's got a whole bunch of curves which decides how this system will back off when you don't need full capacity. Again, you don't need to worry about that. The only number that I would suggest, if you have information, is you change this. If you don't have any information, leave it at that. Say that your system is 3.3 COP at design conditions. That's all you need. Okay. So because it's a heat pump, there is a heating cycle to it. And then this heat recovery is when it is doing this. I told you that some of these systems can do simultaneous heating and cooling. Okay. So this system can do that. Now that VRF system is connected to a series of zones. Okay. And I've got here a zone group, which has got all the ground floor zones on it. Okay. So when you see the system at the overall level, you'll only see one zone, but it is a zone group. If you double click on that zone group, it will tell you I have 6 zones on that outdoor unit. Okay. And if you set it up, it will automatically size the indoor unit for the load that indoor unit will see. So it will auto size each one to what it needs to be. Okay. It's very clever that way, right? You don't have to worry about it. As long as it's the same type of system and it's connected to one outdoor unit, it will do the sizing for you. Now, you can change which zones you want to condition using this ground floor unit, right? If you release some of these zones, they'll be available to put into some other system. If you release zones from other systems, you can put it into this system. So you can mix it up, right? For example, you might say that, okay, I want to put all the south-facing zones on one outdoor unit, or all the core zones or internal zones, I want to put on one unit. So you can have an outdoor unit which does all the core zones. You can have another outdoor unit which does all the east-facing zones, etc. Why would you do that? Well, that depends on how your building is going to be used or leased or rented. You know, they're more flexible around central systems, but you can do that here as well. Okay. If you double click, it takes you one zone deeper or one level deeper, right? You have other things you can set up over there, right? What's the supply air temperature, cooling design temperature when you're doing detailed HVAC. Right now, it doesn't need that because it's going to take the supply air from the HVAC tab. But if you were doing more detailed design, you were interested in doing humidity, CO2 control, all of those things, then you go into detail, and then you have to do more work. So you got to decide what you want to do, right? If I go in one more level and I click inside the system itself, you can see it's coming into the VRF system itself, right? In this place, if you open that box up, you can see here it's representing all the components. There's a cooling coil, there's a heating coil, there's a fan, and there's a mixing box, okay? So you bring in outside air, you exhaust some of the air, you bring in the rest, recycle the rest from the zone, and that's how your system is working. If you read that 6-page note that I've sent through Amanda, you'll see how this can be set up, okay? If you want to change something, you can go into that and you can change several things, okay? So what I did here is I made the availability of the fan the same schedule as in the HVAC tab, okay? I've allowed outdoor air supply to this zone component. So from the activity tab, it knows that it's 10 liters per second per person. It works out for each zone how many people are there. Then it works out how much fresh air, outside air, it's going to bring in. Okay, so there's a complex set of things going on over here, right? And I've explained it step by step in that PDF file that we've sent across to you. You should be able to work step through how you do that. Okay. And for each thing, you actually can go and edit it. This is what Energy Plus is doing. Okay. And anything that Energy, well, not anything, but most things that Energy Plus is making available, you have access to as in the DesignBuilder front end. But one other thing to remember is that now you have two representations of each zone. Okay. Over here, you have the fabric representation. So if I went back here, that's the fabric representation. So that tells you what is the construction material, what kind of glass I'm using, how much insulation I've got, what kind of shading is there, how many people are there, how does the people load vary, all of that stuff is coming from here. Okay. The same thing, all these zones, internal zone, north ground, south ground, you can see them here. Okay. They look a little funny because all the spaces have been, or the dashes have been replaced by X's, but they're the same one. So this internal ground is equal to this internal ground HVAC zone representation. Okay, so there are two separate representations of the same zone. Don't get confused. It's the same in any simulation system. If you look up IES or Trinsys or whatever it is, they have a building envelope representation or a building fabric representation, and then there's a HVAC view of the same one. Okay. So if I open up the other zone groups, you can see exactly the same zones are represented. Okay. Now, what I'll do is I'm going to do a simulation again for the same 1 month. And now we can see there will be numbers for the fan, for the compressor, cooling coils, and so on. So let me run this simulation here. Okay, I'm going to do the same month. And typically I don't look at the daily values. I find them not very useful. I look at the hourly values or for the monthly values or whatever the time frame that I'm doing it for. Now you can decide what all to report. Okay. Now, because I'm interested in the HVAC bits, what I did is in the tables that I've asked it to report, I removed many of the fabric things, and then I'm now looking at HVAC, sizing summary, components, outdoor air, system summary, and looking at the monthly reports. Again, I've removed many of the fabric reports, and I'm putting now consumption electricity, peak use for electricity, the direct expansion system reports, coil reports, fan reports. Now there's no pumps here, but if I had a pump, I would put a pump in. If there were chillers or boilers, I would ask for that as well. Okay, so you can adjust what you get out of that. So let me run, oh, I don't want the simulation manager, back to general. Okay, so now it's going to do a second simulation. In this case, it's going to model all those bits and pieces that we've described. You won't have any more numbers in the district heating and cooling, but now you'll have electricity. Okay, and I want to show you a couple of things so that you don't get confused. Now, a model takes longer to run depending on how complex the fabric is. So what is the model doing? First, every hour it's working out what is the amount of energy it needs to bring that space to the comfort condition that you specify. Okay. In this case, I specified a thermostat of 23.9 for cooling. So it works out how much energy it needs to extract, how much heat it needs to extract from each space to get there. Then it works out, how much energy the fan needs to put in, how much energy the compressor needs, and so on to deliver that cooling. So now it's looking at both thermal energy and electrical energy. Electrical energy to run the compressor motors, to run the fan motors, etc. And the fan's kind of working out how much supply air it needs to provide, what temperature it needs to provide it at, and so on. Okay. So it's a whole complex process. Sorry, I don't need to load the results. Remove that. And again, I will look at the results. And as before, it's coming up on my second screen. This time it's taking a little bit longer because there's more things that it's trying to put out. Here we go. So in the HTML file, if I go and look at it now, there's no more energy for district heating and district cooling. Instead, I'm getting, okay, so the electricity used for cooling is so much, 12,691 kilowatt hours. Here's lighting, here's equipment. Now I've got a number for fans, okay? And you can see my fan energy is actually very small compared to the cooling energy. And that's because when you have an indoor unit, it's quite a small fan, okay? It doesn't need to push very hard. It just needs to recirculate the air in the space. So that's the fan energy used in these systems is typically quite small, but that affects comfort, okay? You really can't do a very large space with one of these indoor units. It's limited to what it can do. You can put a little bit of fresh air in, you can't put a lot of fresh air in. You can't have an economizer cycle, as they call it, right? So those limitations are there. If you go now to the hourly results, okay, and now I'm going to drag this stuff here. You can see what it's doing. It's plotting what each coil is doing, okay, and it's plotting what each fan is doing. So if I plot the fan energy, this is electrical energy, then you can see what this fan is using. It's only using 75, 77 watts when it runs. Okay, it's quite a small fan, it's an indoor fan in here, right? It's also looking at the pressure, the efficiency of the motor, all of those things are in the fan description. If I look for the indoor unit, hang on a minute. That should be at the bottom here. Yeah, here we go. If I look at indoor units, then it tells me what it's using. If I look for the watts, okay, so it'll give me the electricity rate and it will give me the thermal rate. You just have to find where it is that you're looking for. So these are all the indoor units, and compared to that 70 watts, this will be higher. Okay, so you can see the fan energy has almost disappeared. Okay. Oh, that's the outdoor unit. So it's doing, this is the first floor outdoor unit. So it's doing all the first floor zones. And you can see that. So it is using here 25 kilowatts, where the fan was using only 70 watts, 77 watts. So you can see that's kind of almost disappeared, right? And if you want to know what was the hourly COP, it will actually tell you that. You can pick it up and plot it. Okay, I won't do that now, but you can explore all of that. So this will tell you the thermal rate. So we're looking at the first floor unit, outdoor. So I'll plot the outdoor unit first. This is the thermal energy. The other one was electrical energy. So this is the thermal energy for cooling it's delivering. but it's using only so much electricity to deliver that much thermal energy. Okay, that's the COP, right? Your COP is greater than 1 because you're not comparing the same unit. You're comparing thermal energy on top and electrical energy on the bottom. So for every unit of electrical energy that you put into this system, you're getting, at this point, you're saying about 2.5 times that. So your effective COP at that hour is about 2.5. Okay, so it's like a multiplication factor that you have. And then you've got all the other bits. Okay, so you can look at the indoor units. You can plot the indoor unit usage. You only need to plot this stuff if you have a problem and you want to diagnose what's going on. If you don't need that, if everything is working correctly, you can simply go to the summary sheet and pick up the numbers here. Okay. Now, if you remember, I told you that if you go to File, not here, sorry, in DesignBuilder, if you go to the File and the folders, in the Energy Plus folder, all these results will be there. And you can, sorry again, you can pick up all the files from here. So there's that HTML file. There's a CSV file, which is exactly the same numbers. You can put them into an Excel sheet. ESO file has got all the hourly results, which is what we're looking at. If you just want a particular value, say you just wanted the values that we plotted, then you can actually dump them into a spreadsheet by saying save. So then only these two values, these three values that you plotted will go into the CSV file. So it makes it a bit easier to do some analysis. Okay. Now, that's a very fast fly through, and I'm sorry we don't really have the time to do much more than that, but I'd like you all to go back, take a simple shoebox model, don't make it very complicated, just 1 or 2 zones maximum. Work through the VRF part, okay? Make sure it's working correctly. Try something. Put better glazing, more insulation, some shading. Look at both the load changes and the energy changes, and then try to say, well, why is it doing that? Is it working correctly? Is it not working correctly? Okay. So I'm going to leave it there. If there's any quick questions, we'll take it. And then I'll show you a little bit about central systems. Okay, again, that's a vast amount of knowledge, but I will show you a 3 chiller, 2 cooling tower, 5 AHU VAV type system, which I put together for a 10-story building. Okay.
So PC, we have ran actually already 15 minutes
Over time.
Over time.
Okay. Well, I mean, the question can be that if there are people who really want to do central systems, we can do another session.
Right.
People who are doing VRFs, I think this will get them across.
Yeah. So we also have another session next week, right? So we could start with this next week and then continue with the.
Okay. Now next week, what date is that?
Next week is on 19th.
Okay.
Yeah.
That's fine.
Yeah. So Sunita says it would be great if we could have a central system. Yeah, I mean, definitely we will, but since today we have really run out of time, so I think, is that okay, PC?
Yeah, it's okay. What I'll do, I'll take 5 minutes, right? I'll just open a file so they can at least see what we are aiming for. Okay, so in the meanwhile, if there's any other questions, yeah.
Vishal also says if this can be done now would have been great. Just a glimpse would do.
Okay, we'll give you a glimpse.
Right.
Well, there's 27 people who are still interested, so at least we can. We
Great.
started with 48,
Yeah.
we lost 20. So, okay. So now in DesignBuilder, there's a bunch of templates. So you can start by, when you get to the detail system, you click on a template and you can pick a system that's closest to what you want. And it'll come sort of pre-wired. There'll be one zone group, one HU, one chiller, one boiler, one everything, and that'll work. Okay. Now you have to adjust it to what you want, but at least you have a initial system that will simulate as soon as you start. Okay. So what I've done here, here's my 10-story building. But what I did is I didn't model all 10 stories. I modeled the top floor, the bottom floor. The bottom floor is just about a car park. Then I think I did the first floor, then one of the middle floors, and I multiplied it by 7. You're better off doing all 7 floors, but for what I did, that's sufficient. And I built the air conditioning system. Okay. And this runs quite well. So you can see here, very complicated, but it's not that complex.
You're
Okay?
not sharing your screen?
Oh, I'm not, sorry. Hang on. Let me go back. Not the best way of doing that. Okay, tell me when you can see.
Yeah, I can see now.
Okay, all right, good. So I was saying this is, I modeled the top floor, one of the typical floors, multiplied it, a bottom floor, then a floor just above the car park, and I've got them all listed here, right? This is my system. So when I model the system, you can see there's a bunch of things here. Okay? So again, it looks complicated. It is complicated, but it's logical. So you can work your way around it. Okay. We have a water-cooled chilled water system using VAV boxes, that is variable air volume boxes in the zones being supplied by air handling units, central air handling units. That's the full description of this system. So obviously we have a chilled water loop, we have a hot water loop, we have air loops, then we have zone loops. Okay, so 5 different loops. And you can recognize all of them here. Here's your chilled water loop. Here's your condenser loop. So that's your cooling tower, making your chillers efficient. Here's a hot water loop. There is 1, 2, 3, 4, 5 central air handling units or air loops. And for each of the AHUs, there is a zone group. Okay. So if I look first at the chilled water loop, and that's over here. Okay. So you can see here chilled water loop. And DesignBuilder will show you just the chilled water loop. Okay. If you open the box up, then the chilled water loop has got 2 sides to it. Okay. There's a supply side. So there's something that makes chilled water and supplies it to the building. Okay. And then there's a demand side. So something is demanding chilled water. Okay. So the supply side, you can see there's a cross next to it. The supply side has got 3 chillers, 1 controller, and 3 pumps. So if I go to the supply side, if I click on the supply side, then it enlarges that, only that part. You can see here I've got 1 low load chiller and 2 larger chillers. And each chiller has got its own pump. And the whole of the loop, that's the chilled water header. So there's a supply header and a return header. The supply header goes to the building and the return header comes back from the building. Okay. And then as it goes out of the supply header, I've put a controller. Okay. And that controller basically sets the temperature at which the water is going to go out. So these 3 chillers and those pumps have to modulate to provide me with 6-degree chilled water. That's what I've set up. Okay. If I went and examined any of these things, I could either click directly on that, or I could go and click on over there. You can edit that. So if I want to look at what's inside here, you can see chiller number 2. Okay. It's auto size, so it works out. But I've told it that the sizing factor has got to be 40%, 0.4 of the total load. So it works out what is the total load, and then it sizes for me 3 chillers, 2 of 0.4, 40%, 40%, low load chiller of 20%. It'll auto size it for me. Okay, again, very few programs can do that. Energy Plus with DesignBuilder, you can do that. Then I've got some temperatures here. Okay, what's the chill water leaving temperature? 6 degrees centigrade. What is the entering temperature from the cooling tower? 29.5 degrees centigrade. Okay. What's the lowest chill water that this chiller can provide? I'll put 2 degrees centigrade there. Okay, these are all check figures. How does the chiller part load performance work? So when I don't need 46, when the outside is not 46 degrees, I don't need 1,000 tons, I only need 500 tons. What does this chiller do? Okay, and there are 3 curves here for each chiller, which decide how this part load performance is going to happen. Okay, again, too much detail for you guys, but for the guys who know mechanical engineering and want to learn about it, it's very interesting. Then these 3 are quite important. Okay, what is the minimum of its capacity that the chiller can run at? Okay, and now most manufacturers will tell you, oh, 10%, no problem. Okay, at 10%, the COP is horrible. It's using something called hot gas bypass. They never tell you that. Okay, so you want to talk to some practical engineers and they'll tell you, oh, I never run a chiller below 20% or 25% or 30%. Whatever it is, put it. Okay, I put 30% here, but modern chillers, you can go down to 20% quite easily. And they are stable at that 20%. Okay, so then you have a way of saying, okay, when my low load chiller is running and it's running at 20%, okay, if I have 1,000 tons and this is only 200 tons, then it can run at 20% of 200 tons. That is the smallest capacity that I can meet. If my building needs less cooling, then I'm in trouble. Okay, if it's anywhere in between, no problem. The chillers can go up and down and work it out. If I run a simulation, I can look at each chiller and see where it's running at. I can see each fan in the air handling unit and see what it's doing. It's a variable air volume system, so you can watch the main fans go up and down. You can see what's happening in the VAV box. It's very, very powerful. But with that powerfulness comes a lot of flexibility and a lot of opportunities to provide garbage. Okay, so whatever you do, keep it simple, keep it really conservative, get practical numbers, because you can make your systems meet outcomes. We've done it. We worked on jobs where you do that. Okay, so that's a chilled water loop. I'll close it off. This is an air loop. So this is an AHU. Again, same thing, demand side, supply side. Supply is what the AHU is doing. It's supplying cold air, right? I've got a controller there. That controller depends on the type of system you're using. If you've got a multi-zone unit, it has different controllers. You've got a VAV system, it's got different controllers. It's got different limits that you can set. Okay, you can add things onto the AHU, right? So you can add humidifier, you can add evaporative cooler, all those things you can explore, and you can drag it and put it in here. Okay, so a lot of opportunities are there. There are some things you won't be able to change. If you say that it's a VAV system, you can't put a constant volume fan. It doesn't let you. Okay, so there are some fail-safe arrangements there. There's a set point manager, which I said will be very much dependent on what kind of system you're using. Okay, this thing called warmers is a high select system, so it will vary the supply air temperature, so it just meets the load with the zone with the highest cooling load. Okay, so and then it will vary the supply air temperature within a certain range. Okay? And you can examine all the different controllers that's available, and you can choose one that's appropriate. Now you need to know which controller is appropriate for which system. Again, you need to talk to an air conditioning engineer to find out what works. Okay, some things just don't work together. That's when you can get some crazy results, or you can even, at the worst case, you can cause your system to crash because it doesn't know how to handle the two. DesignBuilder kind of limits it by kind of not allowing you to choose, some inappropriate combinations, but sometimes it can't do that. There are so many combinations possible. It's not possible to do that. Here's your condenser loop. So cooling towers, each cooling tower has got a pump, very much like the chill water system. There's a supply side and a demand side. And if you go to the supply side, then you can see cooling towers, fans, pumps, controller. If you went and looked at a pump, then you can see how it's set up. Okay, it's a constant speed pump. It's auto-sized power consumption, but you've got to tell it what's the head, what's the efficiency, and so on. And the defaults are not always appropriate. Okay, so you must look at that. You must know what's happening over there. In the zone group, now we're using a VAV system. So this VAV system, this VAV register, variable air volume register, has got a reheat coil on it. Some don't, some do. Your system, you can decide which one you want. You've got all these components over there. So if you've got a radiant heating system, you can put it there. Chilled ceiling, you can put it there. Zone exhaust fans, all kinds of different options are available over there. You got to put the right thing into the zone. Okay, so at this point, I've got a variable air volume box with a reheat coil and a extract. Okay, relief air. So you supply and you take away from that zone. And at each level, by the way, you get to be able to edit. Okay, depending on where you are, you get different things. And that's all within the Energy Plus simulation system. So if you go into the actual VAV box, you can then tell it, okay, what's the maximum reheat temperature? What's the minimum turn down? How much can the variable air volume box close to? Okay. Now, if you don't give it the right numbers, you say, oh, it can close all the way down. Actually, you can't go all the way down. Your H, you can only turn down a certain amount because the fan can't turn down beyond a certain amount. If you need to provide some cooling to a number of zones, then you need to be able to provide useful cooling to the last zone, the zone that's the furthest away on the duct. If you don't have any air pressure there, then it's useless. So you can't turn your fan any less than that. You need to know what that number is. Nobody will be able to tell you, so you got to take a guess. Okay, or you got to do a detailed design, and somebody's got to add up all the pressures and tell you, okay, at that point, I need so much pressure, and that's equal to so much percentage of the design flow. Then you can set it. Okay, so typically they'll tell you, 50%, 60%. That's good. If they start telling you numbers like, oh, you can drop it all the way down to 20%, that's rubbish. Okay, you get fantastic outcomes on the simulation, you will never get it in reality. Okay, so these are all things that you may need to consider. The software will do whatever you want. Garbage in, it'll give you garbage out. No problem. Okay. Whether you'll come anywhere near that in reality, that's a different question altogether. Okay. So
there's a question in the chat window.
yeah.
Maybe we can take this up, and I'm sure we will be, covering this in detail again in the next session, right? With solar systems, solar PV systems, right?
Yeah.
So, yeah. So question is where, sorry, you were saying something.
No, go ahead.
Yeah, so question is where can we find this 10-story building with 5 AHU that you're showing in DesignBuilder template?
You can't.
Can you share this example model to explore? Yeah.
No, I don't think I want to do that. There's too much intelligence in that model. But
Right.
let me take 1 minute to show you something that might be useful for you. Okay. So you load the HVAC template, right? And here are all the HVAC templates already built into DesignBuilder. If you take VAV reheat with water-cooled chiller and you press OK in whatever building you want, it will give you one chiller, one cooling tower, one boiler, one air handler, one zone, all connected. Okay, so you can start exploring using that. And I'm going to put all the zones onto that one AHU, right? And if I say finish, it is overriding my system. And here's my template. At this point, you can simulate. It's all connected, all right? But you must go and look at all the defaults and agree whether that's correct or not. Just remember, the DesignBuilder is written by European engineers, so many of the defaults are actually not appropriate for the tropics. Okay, the design loop temperatures are different. They have constant problem with freezing, so they use glycol instead of water. We use water. We never get below 0 in most of our cities. Okay, so those things you need to change. We don't use boilers and reheat coils, so you may need to change that. But at this point, this will run. And that's probably the best way for you to explore. Pick a template that is closest to what you want. Okay, and there's quite a few templates here. And then apply that template and then work from there. Now, somebody was talking about ASHRAE 90.1. There are 10 standard systems that ASHRAE has, now 13 now. And if you know the description of those systems, you can pick one of those and you can work from there. Okay, Americans don't like chill water systems that much. Well, they do in large buildings, but in their medium buildings, they use packaged units. So they'll crane an entire air-cooled system on top of the roof, cut a hole through, put some ducts down, and they'll do that. So you'll see a lot of their packaged systems. Okay, that's really just everything is in one box. It's an air-cooled system, sits on the roof. You drill a hole, put a duct, and off you go. Okay, what we are looking at is probably system number 7. Okay, so there's a whole bunch of templates. Explore. Okay, yeah, I can't give you that model because it's taken us a long time to set it up, and we use it a lot in our consulting work.
Yeah, okay, cool. So we'll catch up again in the next session, which is on 19th, the coming Sunday, where PC will cover more about the centralized system again and solar PV systems.
Yeah, so we'll do, what we can do is that we can do the first session. You guys have seen this, so try and maybe come prepared with a few questions. And what I can do is I'll take this system that we saw here. We'll build it from scratch. I'll put a template on and I'll show you how to connect. It's pretty easy. You can work it out, but I'll show you how to make, say, 2 chillers and 2 AHUs and so on. So then it's easier for you to do that.
Yeah, so for everyone, this video is available live on YouTube. Please feel free to look at it again once again, and prepare your questions for the next session, and we can discuss more in detail. Right. All right, so it's lunchtime for here. So we'll meet again in the next session. And yeah, thank you all for joining. Thank you, PC, so much. I mean, it was a very detailed information, lots to take in. Especially in the poll question, the question was, have you had chance to model a HVAC system? 86% of the attendees had answered no. So it must be really big thing for, yeah.
Yeah,
And a
you
lot of,
must work with an air conditioning engineer. You must. Okay.
right, yeah.
If you're doing a simple VRF type system, you can model it without too much difficulty because I've given you a fairly detailed thing. But anything more advanced, you must work with an HVAC engineer. They will at least guide you in, you can at least ask them questions and push them to give you an answer, and then that'll help you. Right?
Okay, see you next time in next week. So yeah, thank you. Thanks, PC.
All right.
Thank you.
Thanks, everyone.